So we are moving on to the second part of improper integrals. The first part, I indicated a resource by the Weber and Edwin Pessel, that is calculus. Today I'm adding two more resources, that is calculus by James Stewart, and then advanced engineering mathematics by K.A. Stroud. Great. Now I want to look at the type 1 of improper integrals, and we are going to treat ourselves to three definitions. So A, we are saying that if this expression, the integral running from a to t f of x dx exists for every number t greater or equal to a, then we have this to be true. Then this integral running from a to infinity f of x dx will be written as limit as t approaches infinity, integral running from a to t f of x dx. And if this limit exists, or as we will say, if a finite number can be obtained, then that is fantastic. B, this time, if the lower limit is negative infinity over here, it was positive infinity at the upper limit. If we have the whole of this and it exists for any number t less or equal to b, then we also have this expression to be written this way: limit as t approaches negative infinity, integral running from t to b f of x ds. If this exists, or if a finite number can be found, then we will say that a and b are said to be convergent, or we call them convergent functions. And if the limit does not exist, then we say that they are divergent, right? So if a finite number is obtained, it is convergent. If we get infinity positive or negative, then we say that the limit does not exist and it is divergent. Now, if we look at this expression and that expression, and they are all convergent, if this and that are convergent, then we define integral running from negative infinity to infinity f of x ds to be equal to this, running from negative infinity to f of x ds plus integral running from a to infinity f of x ds. Then we'll write it this way. So kindly take note of these three definitions. So A, B, and C. All right, so we want to look at some examples. The first example is giving us the sketch of y equals 1 on x squared. And this shaded area is what we are going to compute. And so we, for example, we can start from 1, or we can give it a common letter A. So 1 to infinity. So we are saying that this area is finite. When we compute it, integral running from 1 to infinity, we shall get a number, a finite number. And so we'll say that the area is finite, and therefore this converges. Now, for this one, y equals 1 on x. Let's say 1 to infinity, or we can give it a to infinity. Then when we compute this, we'll not get a finite number. And so we say that this is an infinite area. Great. Now determine whether the integral running from a to infinity f of x dx is the limit as t approaches infinity of the area under the graph of f from a to t. So the a can be any number in question 2. So let's see how we can grapple with that. We are saying, according to part A of our definition, integral running from 1 to infinity 1 on x dx will give us limit as t approaches infinity, the integral running from 1 to t 1 on x dx. So when we integrate 1 on x, we shall get ln x in the modulus. Then the lower limit and the upper limit will be t as t approaches infinity. Great. So when we integrate, we now slot in our limits. So we shall get the upper limit being ln t minus 1 Now ln 1 goes to 0. So when we apply our infinity, so ln infinity will give us infinity, so we shall get infinity. So our conclusion is that the limit does not exist, and our function is divergent. It's divergent. Fantastic. So let's move on to the next example. Determine whether the integral, as we have it here, is the limit as t approaches infinity of the area under the graph of f from 1 to t. That is in question 1. The first one we did was on this, and this is the question 1. Okay. So question 1, we have it as 1 on x squared. So let's go back to the question and do it. So we have our integral running from 1 to infinity, 1 on x squared dx. Then we can write it as limit as t approaches infinity, the integral running from 1 to t, 1 on x squared dx. So let's try and simplify this. So 1 on x squared can be written as x raised to the power negative 2. The next step is that we try to do our integration. So we add 1, we shall get negative 1, we divide by negative 1. So we shall get negative x raised to the power minus 1. Now, we can rewrite it from indices this way. So limit as t approaches infinity, negative 1 on x within the interval. Now, so first, we use our t. We'll put our t here. You'll see that we shall get 1 on t. And that is actually the upper limit. And then when we come to the lower limit, we put in 1. Now let's remember that this negative will meet another negative, so it will be positive. So that's why we have the 1 here. Then we brought this 1 there. Right. Now, as t approaches infinity, it will be 1 over infinity, and that will crush the 1 on top to be 0. So we shall get 1. And so we shall say that it is convergent. So 1 on x squared is convergent. The area is finite. Fantastic. Let's move on to another question. We want to evaluate the integral running from negative infinity to positive infinity, 1 on 1 plus x squared dx. So we are going to use the definition in C. Over here, we'll split it. So let our A be equal to 0. Let's go back to the definition at C and C. So this to A to that. So we want to pick out A to be 0, and that's between negative infinity to positive infinity. Fantastic. So let's go back to the question and see how we can understand it. So we are using the definition C. Now, over here, we want to make use of the trig identities. So we say that let x equal to tan theta. Now let's differentiate both sides. So when we differentiate, we get dx, let's differentiate with respect to theta. So you get sec squared theta d theta. And so now I want to go back and do the substitution. So you have now expressing that in what we have at C. So the whole of this will be expressed this way. Integral running from negative infinity to 0, 1 on 1 plus x dx, plus integral running from 0 to infinity, 1 on 1 plus x dx. So we shall do them individually. So we shall do this first. When we finish, we shall do this one. Now, we are going to do the substitution. So in place of our x, we put our tan theta. So we shall get tan squared theta. And then our dx over here is sec squared theta d theta, so we put it there. Now, let's remember that 1 plus tan squared theta is sec squared theta. That is the identity where we have 1 plus tan squared theta giving us sec squared theta. So we do that substitution. So this will divide that, and we shall get 1. And so that takes us to the next step, where we're still repeating our limit as t approaches infinity. So we shall get 1 here. And when we integrate, because we are doing that with respect to theta, we shall get theta here within the interval. Right. Now, the next step is that we need to get our value theta in terms of x. So we go back to the representation with it. So we are making theta the subject, so theta will be equal to tan inverse of x. Theta over here, so we say note. So theta will be equal to tan inverse of x. So we shall be using this one in place of that. Fantastic. So let's go back to the point. Right. So that's why we have this one. Now this time we are not going to slot in our values. So in place of x, we put our t. In place of x, we put our 0 as the lower limit. Now tan inverse of 0 is 0. So move on to tan inverse of t, which is now infinity. And so we all know that because of the asymptotes in the sketch of the tan function, we shall get pi on 2 for that. Great. And so similarly, when we go through the same thing by the same representation with the limits different, then we shall get the whole of this, and that will also give us tan inverse of our x. So tan inverse of x, and then we'll put in our values here. So tan inverse of 0 minus tan inverse of t. So this goes to 0, and then the whole of this tan inverse of infinity will give us pi on 2. Remember, because it's negative, we shall get negative pi on 2. So minus minus gives us plus. So it means that for that also, we shall get pi on 2. So when we combine the two, that is integral running from negative infinity to infinity, 1 on 1 plus x squared dx, we shall get pi on 2 plus pi on 2. So that gives us pi. Great. So we shall say that the given integral or integrand is convergent. Given integrand is convergent. And that does it. So let's look at the sketch. So 1, that is y equals 1 on 1 plus x squared. That is the sketch. So this is the area under discussion. Negative infinity to positive infinity. And so when we evaluate that, we shall get pi as our value. So let's go back, take your time and look through it again. I've done it from first principles. We are evaluating this and went through it this way. So revise your trigonometry and use them appropriately. Revise your trig. So similar to the same for this one. All right. So that does it for this question. That does it for this question. All right. Fantastic. Let's look at some exercises. Determine whether each integral is convergent or divergent and evaluate the convergent ones. So we have question 1, question 2, question 3, question 4, and question 5. So I want you to look at them again. Take your time and look at them. Great. So thank you so very much for your time. Bye for now.